Okay, great. So what I will be talking about is something that sounds a little bit theoretical, but I think it might have relevant implications from the point of view of practical approaches for earthquake early warning. And so I know that you know these things much better than me, but I need just a little bit of background before starting. So one of the biggest issues of an earthquake early warning system is how can we estimate the final magnitude of an earthquake while the rupture process is still ongoing and we don't know how it's going to propagate. And this is especially true for the case of very large events for which the rupture process and the slip distribution can be very complex. So how can we estimate the final magnitude just by looking at the beginning of the rupture process? So what we generally do in the context of early warning is we measure some parameters along the first few seconds of signal. Typically 2 or 3 seconds of P wave are used. And this can be amplitude parameters or period parameters, and they have been shown to be empirically related to the earthquake magnitude. So now I'm going to focus on one of these parameters, which is the peak displacement. The peak displacement is the maximum amplitude of displacement in absolute value, and it is related to the magnitude and distance through a sort of attenuation relationship. So what we've done is very easy. We collected some earthquakes in Japan with magnitude between 4 and 9, and we collected data from 0 to 500 kilometers away from the source. So for each station, first we manually picked the P wave arrival along the vertical component of acceleration. Then we double integrated and applied a high-pass filter to get displacement. And then we measured the peak displacement amplitude starting from the P wave and then expanding the time window up to the arrival of the S wave. Then, for each event, we computed the average peak displacement curve as a function of time using all the available data at each time. And of course, before computing the average, we corrected each PD value for the distance effect. So here is an example of how the peak displacement looks like for a single event. So we have time from the P wave arrival. Here we have the amplitude, and the color is showing the number of stations used for the average. So as you can see from the color, while the time window increases, the number of stations used for the average decreases. And this is because we have to exclude those stations where the S wave has arrived. So when we look at the shape of this function, we can clearly recognize that there is an initial increase, a final plateau level, and then there is something in the middle which we call the transition phase. Then, to reproduce the shape of this function, we used a very, very simple model, which is a piecewise linear function. So basically, for each event in our database, we computed the average peak displacement curve as a function of time. Then we fit data with this model, and we estimated 5 parameters. The first corner time, T1, the second corner time, T2, the slope of the first line, the slope of the second line, and the final plateau level. And then we looked at the scaling of these parameters with magnitude to understand whether there are similarities or differences among the events. So how do we expect them to scale? So this is just a theoretical slide showing, so this is the synthetic moment rate function computed using the circular fault model of Sato and Hirasawa. So let's assume that this is the source. These are for 2 different magnitude earthquakes. So let's assume that this is the source. If we measure PD on this function, this is what we will get. So PD increases until the peak of the moment rate function, and then it becomes stable. So we should expect somehow that the saturation time, which is called T2, is somehow related to the source, to the magnitude of the event. And this is, in fact, what we found, because we found that the second corner time, T2, scales with magnitude. It increases with magnitude in a log linear scale. And we are talking about 2-3 seconds for a magnitude between 4 and 5, and 30 seconds for a magnitude 9. And similarly, also the plateau level scales with magnitude, but this is again something that we expected from the theory. What is interesting, and I think much more important in the context of early warning, is that also the first corner time increases with magnitude. And just to give you an idea, we are talking about 0.2, 0.3 seconds for a magnitude between 4 and 5, and 2-3 seconds for a magnitude 9. And the slope of the first line decreases with magnitude. So small earthquakes begin with a high initial slope, while the peak displacement increases very slowly at the beginning for large earthquakes. So now if we combine these two results, and if we look at them in terms of the model that we have selected, this result seems to suggest that the way small and large earthquakes begin is different from the very beginning of the rupture process. And this can be related to the nucleation phase, and in particular, this can be related to the size of the nucleation phase before the dynamic rupture is triggered. But now I don't want to go into the details of the theory behind that. For those of you who are interested, maybe we can discuss later. But I would like to focus on the practical applications of these results. So this is a figure showing how the peak displacement changes as a function of time for different magnitude. So you can clearly see how the slope is changing when passing from magnitude 4 to magnitude 9. So if we were able to measure the slope in real time, we could rapidly discriminate a small event from a large event. Now the question is, how quickly we can do that? So this is another example showing that we could actually measure the slope even within 1 second. So the blue dots show the slope measured within 1 second for earthquakes with magnitude larger than 6. So as you can see from this picture, the initial slope can be very well constrained even within 1 second. So 1 second could be enough to discriminate a small event from a large event. But the problem is that we need to develop an algorithm, a very efficient algorithm, which is able to measure the slope in real time and which is able to stop as soon as the slope is changing too much. And to be honest, having looked at the data, I see it quite challenging in real time. And then the next question is, how many data do we need to do that? And again, if we are able to stop when the slope is changing, even few data can be enough to constrain the slope. What I mean is that if we look at this model, if we are able to stop precisely at this time when the slope is changing, even 1 station or 3 stations can be enough to constrain the slope. But again, the problem is how to stop here at this time, because the change in the slope is not really is not so evident sometimes. And then I just want to conclude just by giving what can be the future perspective of this work. So the idea is that we start measuring PD as soon as we get the P wave, and then as soon as the slope is changing, we can rapidly discriminate a small event from a large event. Then we keep on measuring PD, and once that PD gets to its maximum value, we could also provide an approximate estimate of the duration, of the expected duration and size of the rupture. And this is because of the correlation that we have seen before with the moment rate function. So the saturation time is possibly related to the half duration of the moment rate function. So I'll go to the conclusion. So we have seen that PD shows a different behavior between small and large earthquakes. I didn't spend too many time on the interpretations because I wanted to focus on the practical applications, but the interpretation can be related to the nucleation phase. So as for the practical considerations, we should move toward a continuous measurement of PD. So rather than looking at fixed time window, we should look at the way PD changes with time. And if we are able to measure the slope in real time, we could distinguish a small event from a large event, and we could also rapidly estimate the size of the rupture. And I think that's all. Thank you.
Questions? Barry. Wait for the mic. I just had one question. I noticed in the beginning, you're starting from acceleration and you're integrating twice.
Yeah.
And then you're, to get around a lot of the problems that usually occur, that you're applying a high, and you're applying a filter. Is the choice, I mean, are you worried? Could your choice of that cutoff knock out the longer period energy that might help in this process? In other words, might you do better if keeping a little more of the longer periods? I'm just wondering.
Are you worried that the filter is somehow changing these results?
Yeah.
Is this the question?
Within a certain...
Okay,
yeah.
well, I can show you. Well, I tried, this is showing the first corner time and the slope, the initial slope, using displacement, velocity, and acceleration. So basically, the shape of the function is the same, even if I use acceleration data, where no filter is applied.
So this is an interesting and important question of how soon do we know when we're dealing with a very large earthquake. And one approach to the problem is, in California, is to say, if we knew it was on one of our major fault structures, like the San Andreas fault, should we make a different prediction than if we thought it was on some short fault that we'd never seen before? So an earthquake has begun, and we want to know what's the chance it's going to run some very large distance. Do we make a different statement, whether it's on the San Andreas fault or some other fault? And you're suggesting in here that, well, actually, we'd just look at the P wave and we'd make this statement. And kind of mixed up in there is the question, is the beginning of the P wave telling you something about the nature of the fault, or is it telling you something about the nature of the particular rupture that you're looking at?
I'm not sure I got the question. Sorry.
How does this work?
It works fine. I mean, for the
So if the signal has an exponential growth, as your analysis shows, then this slope, B1, is inversely proportional to tau p, this other quantity that has been used in early warning for many years. So isn't that what you need, just a plain old tau p?
So are you referring to the nucleation phase? Yeah. So what I mean is that. Okay. All right. Here we are. So. So there are two ways to explain that the slope is decreasing with magnitude. So let's assume a linear slip weakening law. There are two possibilities to explain that the slope is decreasing with magnitude. One is to say that the strength decreases with magnitude. That sounds unreasonable. And the other one is to say that the size of the nucleation phase increases with magnitude. So earthquakes the ruptures that start in a region where the critical slip distance is larger have a larger probability to grow into a large event. I don't know if this answered the question, but.
Can I ask a question?
Very, very quick.
So the data from the magnitude 9, I assume, is from Tohoku, and from the 7.2, which was the second biggest earthquake, is from Kukapa El Mayor.
No. There are all earthquakes in Japan.
Okay, but how close was the nearest station in each of the cases? And how does that affect the measurement?
So for the case of Tohoku, the closest station was 150 kilometers away from the source. For the case of the magnitude 7, I think the magnitude 7 should be this one. So there are also stations very close to the event.
Okay, now I think we need to move on. Can you ask for? Okay.
From that plot that was the other that you had them on a second ago, so you're saying there's a factor of 20 difference in the initial slope between a magnitude 9 and a magnitude 3? Factor of 20?
Yeah.
The magnitude 9 starts 20 times weaker than the magnitude 3?
Yeah.
I mean, we've been looking at this for decades.
I want to show you, sorry, I just want to show you Yeah, you can see from that. This is a magnitude 4.7, and you can see how rapidly the peak displacement increases. And look at the time scale, which is completely different from the magnitude 9. So it takes 3 seconds, and here it takes less than 0.2 seconds.
Okay.
These are
All right.
data.
Thank you.